On November 5th, 2018, a spacecraft that had already been flying for more than 41 years, launched back when disco was still on the radio and nobody had ever heard the word internet, quietly crossed an invisible boundary 11 billion miles from Earth and became only the second human-made object in history to leave the protective bubble surrounding our entire solar system. NASA's mission team didn't announce it immediately because they needed to be certain first. It took the plasma science instrument aboard. Voyager 2, confirming that the steady stream of charged particles flowing outward from the sun had simply vanished from its readings, replaced by an entirely different, colder, denser kind of plasma that could only be coming from somewhere else, from the vast, mostly empty space between the stars themselves. Once 3 other onboard instruments, the cosmic ray subsystem, the low-energy charged particle detector, and the magnetometer, all confirmed the same basic story independently, mission scientists finally felt confident enough to say it out loud. Voyager 2 had left the heliosphere. It had entered interstellar space, and unlike its twin, Voyager 1, which had made the exact same crossing 6 years earlier in 2012, but did so with a broken plasma instrument that couldn't actually measure the transition directly, Voyager 2 arrived at this boundary with a fully working set of sensors, giving humanity its first ever direct, functioning measurement of what the true edge of our solar system actually looks like. What those instruments found waiting on the other side turned out to be considerably stranger and considerably less understood than anyone on the mission team had expected. To understand why a single aging spacecraft crossing an invisible line in the vacuum of space became such a genuinely significant scientific moment, you first have to understand exactly what that line actually is, and why reaching it took Voyager 2 more than 4 decades of continuous flight to accomplish. Our entire solar system sits inside a kind of enormous, invisible bubble called the heliosphere, created by the solar wind, a constant stream of charged particles blown outward from the sun at supersonic speeds in every direction. That bubble is genuinely massive, stretching roughly 11 billion miles from the sun at its widest known point, encompassing not just Earth and all 7 other planets, but a huge volume of space well beyond even the outer edges of the traditionally recognized solar system. The boundary where that solar wind finally runs out of momentum and collides head-on with the interstellar medium, the thin, cold material drifting between stars throughout the wider galaxy, is called the Heliopause. It's not a hard physical wall in any conventional sense, but it functions as something close to one, a genuine measurable transition zone where the hot, sparse plasma inside the sun's influence gives way abruptly to the colder, denser plasma of true interstellar space. That boundary matters for reasons well beyond simple curiosity about where our solar system technically ends. According to Caltech astronomer Edward Stone, who dedicated more than half a century of his career to the Voyager program before retiring, the heliosphere's protective shield blocks out roughly 70% of the dangerous cosmic radiation that would otherwise come pouring in from deep space, radiation energetic enough to damage the very DNA of every living thing inside it, including, ultimately, us. Getting a spacecraft far enough away from the sun to actually reach and cross that boundary took an extraordinarily long time, even for a mission launched with genuinely audacious ambitions from the very beginning. Voyager 2 lifted off in August 1977, actually 16 days before its twin, Voyager 1, on a mission originally planned to last just 5 years, a relatively modest grand tour past Jupiter and Saturn designed to take advantage of a rare planetary alignment that wouldn't occur again for another 175 years. Voyager 2 ended up being the only spacecraft in history to visit all 4 of the solar system's outer giant planets, flying past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and finally Neptune in 1989, delivering the first ever close-up images of both Uranus and Neptune that humanity has ever obtained, images that remain, to this day, the only close-range photographs of either planet any spacecraft has ever captured. Once that planetary tour wrapped up, rather than simply going quiet, both Voyager probes kept flying outward, kept transmitting data, and kept slowly, patiently working their way toward the true outer edge of the sun's influence, a journey that would end up stretching on for nearly 3 full decades after their last planetary flyby. When Voyager 2 finally did reach and cross the Heliopause in November 2018, the first genuinely surprising discovery came almost immediately, simply from comparing exactly where and when the crossing happened, against its twin zone crossing 6 years earlier. Scientists had long understood that the heliosphere isn't a fixed, unchanging bubble. It expands and contracts somewhat over the course of the sun's roughly 11-year solar activity cycle, breathing in and out according to researchers' own description, almost like a lung. Voyager 1 crossed the heliopause back in 2012, during a period of relatively low solar activity, while Voyager 2 made its own crossing in 2018, during a considerably more active phase of that same cycle. Given how differently those two moments in the solar cycle should have affected the size of the bubble, researchers genuinely expected the two probes to have crossed at meaningfully different distances from the Sun. Instead, according to researchers at Johns Hopkins University's Applied Physics Laboratory, the two spacecraft encountered the Heliopause at almost exactly the same distance, Voyager 1 at 121.6 astronomical units from the Sun, and Voyager 2 at 119 astronomical units, a difference of barely 2.5 astronomical units, despite exiting through completely different regions of the bubble, years apart, during opposite phases of the solar cycle. That single coincidence, or rather the fact that it wasn't supposed to be a coincidence at all, immediately told researchers that whatever was actually controlling the heliosphere's true size and shape was considerably more complicated than the simple, predictable breathing pattern scientists had assumed governed it. Because Voyager 2's plasma instrument was still fully functional, unlike the broken equivalent instrument on Voyager 1, it delivered humanity's first ever direct measurement of the actual physical properties of interstellar plasma the moment the spacecraft crossed over. That plasma turned out to be considerably colder than the plasma inside the heliosphere, exactly as theoretical models had predicted it should be, a genuine confirmation of decades of prior scientific modeling. But the data also revealed something researchers hadn't fully anticipated, evidence of a slight increase in plasma density occurring just before Voyager 2 actually crossed the boundary, as though the plasma were being compressed right up against the inside edge of the bubble in the final stretch before the true interstellar medium took over. Scientists still don't fully understand exactly what physical process is causing that compression zone to form, and it represents one of several genuinely open questions Voyager 2's crossing raised rather than resolved. The spacecraft's magnetic field instrument delivered what might be the single strangest and most consistently described finding to come out of both Voyager crossings combined. When Voyager 1 had made its own crossing back in 2012, its magnetometer picked up something researchers frankly didn't expect. The direction of the magnetic field on the interstellar side of the boundary appeared to align remarkably closely with the direction of the magnetic field still inside the heliosphere, rather than showing the kind of sharp, obvious directional shift researchers had generally anticipated at a genuine transition between two entirely separate physical environments. When Voyager 2 crossed 6 years later in a completely different location along the boundary, its own magnetometer confirmed the exact same surprising alignment all over again. NASA Goddard heliophysicist Elena Provornikova, reflecting on the broader body of findings that emerged from Voyager 2's crossing, described some of the resulting data in blunt, genuinely candid terms, characterizing certain results as very, very weird, and noting that the anomaly clearly showed researchers needed considerably more data before they could actually explain what was going on. Finding the exact same unexpected magnetic alignment at two entirely separate points along the Heliopause's boundary, rather than treating it as some kind of isolated fluke unique to Voyager 1's specific crossing point, told scientists this was a genuine, consistent feature of how the Sun's magnetic influence interacts with the surrounding interstellar magnetic field, one that existing models of the heliosphere's structure still can't fully account for. Perhaps the most genuinely unsettling discovery to come out of Voyager 2's transition involved the basic question of how sealed off the heliosphere's protective boundary actually is. Researchers had generally pictured the heliopause as functioning something like a relatively solid, if invisible, wall, separating our solar system's environment from the wider galaxy beyond it. Voyager 2's instruments told a different, considerably leakier story. One of the spacecraft's particle detectors picked up clear evidence that a steady trickle of particles originating from inside the heliosphere was actively slipping outward, right through the boundary, into interstellar space, rather than being cleanly and completely contained by it. Researchers at NASA's Jet Propulsion Laboratory offered a memorable comparison to describe the finding, suggesting that if the heliosphere functions something like a ship sailing through the surrounding sea of interstellar space, the actual hull of that ship turned out to be somewhat leaky, separate. Analysis published the following year identified something even more specific. Two distinct porous holes located on the heliosphere's own side of the boundary, regions where interstellar radiation was measurably leaking inward past the protective barrier that's supposed to be blocking it, with radiation levels spiking noticeably higher than the surrounding background, before dropping back down again as the spacecraft moved past each individual gap. The heliopause, it turned out, isn't the clean, continuous shield scientists had generally pictured. It's something closer to a porous, imperfect membrane with genuine gaps that let both particles and radiation pass through in both directions. That porousness helps explain a genuinely important, if slightly less dramatic, discovery about how the heliosphere protects everything living inside it. Researchers confirmed that the boundary region does function as a real, physically effective barrier. a hot, thick wall of compressed plasma sitting right at the edge of the bubble that helps deflect and dilute a huge share of the intense cosmic radiation constantly streaming in from deep space, blocking roughly 70% of it, according to Stone's own estimate. But Voyager 2's data made clear that SHIELD isn't perfect or uniform. It has weak points, porous regions, and apparently unpredictable local variations in exactly how much protection it's actually providing at any given location along its surface, a genuinely important nuance for anyone thinking seriously about long-term crewed space exploration far beyond Earth someday, since the amount of protection available clearly isn't the same everywhere along this boundary. Quick pause here, because if the kind of story where humanity's furthest flung, oldest still functioning spacecraft keeps sending back data that quietly overturns decades of careful scientific modeling is exactly the sort of thing that keeps you coming back to channels like this one, that's precisely the territory we keep digging into. If that's useful to you, go ahead and subscribe. It genuinely helps more of this research reach more people. The mystery surrounding the heliosphere's true shape deepened considerably further in research published in 2022. Years after Voyager 2's initial crossing, when scientists combining data from both Voyager spacecraft with observations from a separate NASA mission called IBEX, the Interstellar Boundary Explorer, discovered that the heliopause itself appears to be rippling and shifting in genuinely unexpected ways, forming oblique angles and asymmetries that don't fit cleanly into any of the models researchers had been working from. IBEX had already captured evidence back in 2014 of unusual brightening in what are called energetic neutral atoms, particles created right at the boundary where solar wind collides with interstellar material, and the pattern of that brightening didn't match what existing models predicted at all. When researchers folded that anomaly together with the full record of both voyage crossings, they found something genuinely striking, evidence that the heliopause had actually changed shape dramatically over a comparatively short period of time, a discovery that helped explain part of why Voyager 1 and Voyager 2 ended up crossing the boundary at such different points in the solar cycle, years apart, and yet still landed at such strikingly similar distances from the Sun once they finally got there. The heliosphere, in other words, isn't just breathing in and out symmetrically the way a simple, predictable model would suggest. It's actively rippling, warping, and shifting in genuinely complex, still poorly understood ways across time. That deeper uncertainty extends all the way to the most basic possible question anyone could ask about the heliosphere. What shape is it actually? Voyager 1 exited near what researchers describe as the leading edge of the bubble, the side facing directly into the direction the entire solar system is moving through the surrounding galaxy. Voyager 2 exited along the bubble's flank instead, a meaningfully different location relative to that same direction of travel. Because both probes approached and crossed the boundary from angles closer to the front and side of the heliosphere respectively, humanity currently has no direct data whatsoever from the bubble's trailing edge, the wake stretching out behind the solar system as it moves through interstellar space, the way a comet trails a tail behind it as it moves through the inner solar system. NASA Goddard researcher Jamie Rankin, discussing the puzzle in reporting from National Geographic, noted candidly that scientists genuinely don't know what shape the heliosphere actually takes in that trailing region, with some models suggesting it could remain roughly spherical thanks to the surrounding pressure of the interstellar medium, others suggesting a long, comet-like tail, and still others proposing something considerably stranger, a shape some researchers have described, only half-jokingly, as resembling a croissant. Solving that specific mystery would require an entirely new mission, specifically aimed at that trailing wake region. And no such mission currently exists or is realistically likely to reach that boundary within most of our own lifetimes. NASA's New Horizons spacecraft, still actively flying outward at more than 31,000 miles per hour, will run out of power sometime in the 2030s, while still more than 1 billion miles short of even reaching the heliosphere's outer edge, meaning the two aging Voyager probes remain, for the foreseeable future, humanity's only actual data points from this entire region of space. Reaching the heliopause itself was actually just the final stage of a longer, multi-part journey through several distinct boundary regions, each one crossed years apart and each one delivering its own separate set of surprises well before Voyager 2 ever reached true interstellar space. Back in August 2007, more than a decade before its heliopause, crossing Voyager 2 passed through what's called the termination shock, the point where the solar wind abruptly slows from supersonic to subsonic speed as it begins colliding with the pressure of the surrounding interstellar medium. Voyager 1 had crossed that same termination shock boundary 3 years earlier, in December 2004, and comparing the two crossings already revealed an early hint that the heliosphere wasn't the simple, symmetrical bubble scientists had assumed it to be, since Voyager 2 crossed the termination shock roughly 1 billion miles closer to the Sun than its twin had, on the opposite side of the solar system. That asymmetry meant researchers already had reason to suspect, more than a decade before either spacecraft actually reached the heliopause itself, that the bubble surrounding our solar system was lopsided in ways nobody had fully predicted. A suspicion the eventual heliopause data from both probes would go on to confirm and deepen considerably further. The specific reason Voyager 2's own heliopause crossing turned out to be scientifically more valuable than Voyager 1's earlier one traces back to a very specific piece of hardware trouble that had nothing at all to do with either spacecraft's actual journey through space. Voyager 1's plasma science instrument, the specific piece of equipment needed to directly measure the density and temperature of the plasma surrounding the spacecraft, had stopped working reliably back in 1980, decades before that probe ever reached the heliopause at all. That meant when Voyager 1 finally did cross into interstellar space in 2012, mission scientists had to rely entirely on indirect evidence, plasma wave measurements, and cosmic ray data to confirm the crossing had actually happened, rather than getting a clean, direct reading of the interstellar plasma itself. Voyager 2's equivalent instrument, remarkably, was still fully functional when its own crossing happened 6 years later, giving researchers their first genuinely direct, unambiguous measurement of what interstellar plasma actually looks like up close, a difference that explains why so much of the detailed physical characterization of the heliopause boundary, the temperature readings, the density compression, the porous radiation leaks, ended up coming specifically from Voyager 2's data rather than its twins. That status as humanity's sole source of direct information from beyond the heliosphere is becoming an increasingly precious and increasingly fragile thing to hold on to, because both Voyager spacecraft are now running seriously low on power after nearly 50 years of continuous operation. Each probe relies on a radioisotope thermoelectric generator, a power source that creates electricity from the heat given off by decaying plutonium, and that power output has been steadily shrinking by roughly 4 watts every single year since launch, a slow, unavoidable countdown that NASA's engineering team has been managing with. Genuinely impressive ingenuity for years now. In October 2024, mission engineers shut down Voyager 2's plasma spectrometer specifically to conserve power. In March 2025, they powered down its low-energy charged particle instrument as well. Voyager 2's cosmic ray subsystem is scheduled to be shut off sometime in 2026, a deadline that engineers have already managed to push back once before, buying an extra 3 years of operation by finding a clever way to tap into a small reserve of backup power originally set aside purely as a safety mechanism to protect the spacecraft's other systems from electrical surges. Suzanne Dodd, Voyager's project manager at NASA's Jet Propulsion Laboratory, put the underlying stakes bluntly in comments to reporters, explaining that without these kinds of deliberate power-saving shutdowns, both spacecraft would likely only have a few more months of usable power left before mission engineers would be forced to declare the entire program over. With the current conservation plan in place, engineers now believe both Voyager probes could realistically keep transmitting usable scientific data from at least one remaining instrument apiece well into the 2030s, pushing the mission's total operational lifespan toward an almost unbelievable 6 full decades in space. Every single piece of data those remaining instruments manage to send back between now and whenever the mission finally unavoidably ends carries a kind of scientific value that simply can't be replicated by any other means currently available to humanity. No other spacecraft built by any nation on Earth has ever operated in interstellar space, and none currently in development is realistically expected to reach that same boundary again for decades to come. Every reading Voyager 2's remaining magnetometer and plasma wave instruments continue to send home represents genuinely irreplaceable information about an environment that took humanity 41 years of continuous spaceflight to physically reach, even once, gathered by a spacecraft that was originally engineered back in the 1970s to last for a 5-year mission to just 2 planets, and that has instead spent the better part of 5 decades quietly rewriting scientific understanding of where our entire solar system actually ends and what genuinely surprising, still not fully explained, physics is waiting in the strange, porous, rippling boundary where it finally gives way to the rest of the galaxy. If you want to see how the ongoing data from Voyager 2, and eventually whatever mission someday follows in its path toward the heliosphere's still unmapped trailing wake, continues to reshape our understanding of where the solar system truly ends, there are other breakdowns on this channel digging into exactly that. Let us know in the comments what you find most remarkable about all of this, the fact that 2 spacecraft launched during the disco era are still sending back genuinely groundbreaking science from interstellar space nearly 50 years later, the discovery that the boundary of our entire solar system is actually leaky rather than a clean, sealed wall, or the fact that we still, after everything Voyager 2 has taught us, don't actually know what shape our own solar system's protective bubble takes. See you in the next one.